Hello, students.
Good morning, ma'am.
Hi, good morning, everyone. See, daily I'm doing one theorem as a revision. And the last class I explained the continuous and bounded functions on the set of all real numbers. Today we prove, am I audible? So today we prove that whenever X is a topological space, whenever X is a topological space, then
Ma'am, is this fourth unit?
what?
Fourth unit, ma'am.
Fourth unit. Just I'm
Okay.
doing the revision now. Yesterday I proved that sum of two continuous functions is continuous. And page number is 44. Just I want to revise these theorems which are important. Then CXR is a Banach space. Banach space means a complete topological space. When you say that a topological space is complete, whenever a Cauchy sequence is convergent. X is a topological space, then CXR is a Banach space with respect to point-wise addition. That means f plus g at x equal to f of x plus g of x, and fg at x equal to f of x into g of x, and alpha f at x equal to alpha into f of x. And we have seen that f plus g is continuous and alpha is also continuous in the last class. CXR is a Banach space with respect to point-wise addition, point-wise addition and scalar multiplication. Scalar multiplication. And what is the norm? Norm is defined by norm of f equal to supremum of x belongs to x such mod f of x. This is your norm. Okay, you have to remember 3 points. Element is less than the supremum, and supremum is less than upper bound. I have discussed while teaching the basics in the class. So with respect to this norm, CXR is a Banach space. Clearly, you know that this CXR, we know that set of all continuous functions on R is a linear space. What is a Banach space? A normed space is a Banach space if every Cauchy sequence is convergent. So what you have to prove? We prove that first thing, what we have to prove? CXR is a normed linear space. That means the norm, whatever you have defined, this satisfies properties of norm. All of you know what are the, when it is a norm, norm f is always greater than or equal to 0. Norm f plus g equal to norm f plus g less than or equal to norm f into norm g, and norm of alpha f equal to mod alpha into norm f. So these properties, first thing you have to prove is a norm, CXR is a normed linear space. For that, take f comma g belongs to CXR. Then in the yesterday we proved that f plus g belongs to CXR. Whenever f and g are continuous, f plus g is also continuous. Now we know that how you defined norm. Norm is defined as supremum of x belongs to x mod f of x. We know that mod f of x is always greater than 0. So since mod f of x is greater than 0, we have norm f is also greater than or equal to 0. So tell me when norm f will be 0? Means mod f of x is 0, which implies f of x is 0. That means f is 0. So you have norm f equal to 0 if and only if f equal to 0. This is the first property of norm. And then what is the second property? Norm f plus g. What is the norm of f plus g? Supremum of x belongs to x mod f of x plus g of x. Kada? Mod f of x plus g of x, or f plus g at x, supremum of this one. So we know that mod x plus y is less than or equal to mod x plus mod y. So you have this is less than or equal to supremum of x belongs to x mod f of x plus supremum of x belongs to x mod g of x. So this is nothing but norm f plus norm g. That is norm f plus g is less than or equal to norm f plus norm g. Okay. CXR, safe side you learn, this is easy only. CXR is a Banach space which is like a problem oriented. Now also find norm of alpha f. What is the norm of alpha f? Supremum of mod alpha f at x, for x belongs to x. This is alpha into supremum of x belongs to x mod f of x. This is alpha into, mod alpha into norm f. So therefore, what do you mean? You have CXR is a normed linear space. This is important for 10 marks. CXR ichina, you have to write like this only. CXC also you should write like this only. Okay. Banach space means it is a complete metric space. So CXR will be a metric space. Is a metric space since the metric defined by d of f of g is norm f of a norm f minus g. So if you, so it is easy to prove that this is a metric and d of f of g is equal to norm f minus g. If you like define like this, you will have d of, no need to prove, just you can prove all the properties of metric. Metric on x, so x is a metric space. Now we prove x is complete. In order to prove x is complete, now we prove capital X is complete. To prove, anyone can tell me what is required to prove now? When a metric space will be complete? Students, are you there?
Yes, ma'am.
Yeah,
Yes, ma'am.
When a metric space is complete. When every
Sequence is convergent.
Very good. Every Cauchy sequence is convergent. That every Cauchy sequence in X is convergent. For that, take one Cauchy sequence. Let Fn be a Cauchy sequence in CXR. Let Fn be a Cauchy sequence in CXR. Then we prove that Cauchy sequence is convergent. For this, let epsilon greater than 0. So what do you mean? Write the definition of Cauchy sequence. For this given epsilon greater than 0, there exists a positive integer n0 such that norm Fn minus Fm is less than epsilon for all n comma m greater than or equal to n0. Okay. So when you have norm Fn minus Fm is less than epsilon, means what do you mean by this? You have supremum of x belongs to x mod Fnx minus Fmx is less than epsilon for all n greater than or equal to, for all n comma m greater than or equal to n0, you have mod Fnx minus Fmx is less than epsilon. So what do you mean by that? This implies whenever this is less than epsilon, you have Fnx minus Fmx is less than epsilon. That means you have Fn is Cauchy sequence in R. In R. But we know that R is set of real numbers is a complete metric space. So this comes in real analysis also. That's why I have decided to teach this also. R is a complete metric space. Means you have sequence Fn is convergent. Is convergent. So every Cauchy sequence is convergent means it is
complete metric space.
Complete metric space. But what else you have to prove? CXR, that wherever this function Fn converges, that is also continuous. You have to prove, because these are all continuous and bounded functions. No, the limit function also you have to prove that it is continuous. So you take limit. So Fn is convergence means limit n tends to infinity, Fnx is equal to f of x. This is very important. We should prove that this limit belongs to CXR. Then only you can say that CXR is a complete metric space. So you have to prove that f of x is convergent. Okay. Sorry, Fn is convergent means Fx is continuous. You have to prove. Okay.
Okay, ma'am.
So if you want to prove, we prove it is bounded also. We prove bounded and continuous. Okay. Now you have each Fn belongs to CXR. You can tell in words, no need to take epsilon and all. Means Fn is bounded and continuous. Means since Fn converges to F, F is also continuous and bounded. So you can say F belongs to CXR. You end like this. Okay, ma, no need to write all this. Okay.
Okay, ma'am.
If you want to prove F is bounded, we prove means you can write that F is continuous and every continuous function is bounded. No, every continuous function is bounded. So hence F is also bounded. In this way, you have to write that CXR is complete. Students, even if it comes in exam or not, just have a glance over this theorem, because in next semester you have operator theory or functional analysis. In function analysis, we are going to study about this kind of functions. So that is the reason I am telling you this is very, very important. Important in the sense not for exam, to study next theories. Okay, is this clear?
Okay, ma'am, clear.
Ma'am.
Yeah. So now let us enter into our separation. See, just let me explain what all the things I have so far we have discussed. See, Afterwards, I will share this notes, Sandy, to you in group or somewhere in the class. Here itself, I will share. Let us revise the things what we are discussed, what we have discussed so far on separation.
Which chapter, ma'am?
Separation only. Separation. Chapter
Okay.
means today I will explain unit 12, but unit 12 requires the previous concepts. Just to go through this. See, I told you yesterday, a topological space, X is called a T1 space. If for any pair of distinct points in X, each has a neighborhood which does not contained in the other. That means you have X is a T1 space. If for any X not equal to Y belongs to S, there exists open sets G and H such that X belongs to G minus H and Y belongs to H minus G. This is a T1 space. Next, a topological space X is called a Hausdorff space. If each pair of distinct points in X can be separated by disjoint sets. Okay, that is for any X not equal to Y in X, there exists open sets G and H such that X belongs to G, Y belongs to H, plus G intersection H is empty.
Fine.
So just let us have a glance what all I have discussed yesterday. Every metric space is Hausdorff space. In a Hausdorff space, any point and a disjoint compact space. You have to remember, otherwise you cannot prove Urysohn's theorems. In a Hausdorff space, any point and a disjoint compact space. This compact space means a closed set only, can be separated by open sets. Next, every compact subspace of Hausdorff space is closed. So a one-to-one continuous mapping of a compact space onto a Hausdorff space is a homeomorphism. Okay, a continuous mapping is known as a homeomorphism. A T1 space is a regular space. All this I have explained in the last class. A T1 space is a regular space if for any X in X and for any closed set A not containing X, there exists open sets G and H such that X belongs to G, A subset of H and G intersection H is empty. Next. All of you, are you able to find the distinction between a regular space, T1 space, Hausdorff space? Any doubt? T1 space is completely regular.
No, ma'am.
Okay. If for any X in X, for any closed set F in X, not containing X, there exists a continuous function and this is continuous function. F from X to 0, 1 such that F of X is 0 and F of Y is 1. So Y belongs to F. Tell me what is a normal space? In a normal space, two disjoint closed sets are separated by two disjoint open sets. And we see what are the properties that we have. Every compact Hausdorff space is normal. Every metric space is also normal. Now see here, a T1 space is a normal space. A T1 space is a normal space if and only if for closed set A and any open set U containing A, there exists open set V in X such that A is a subset of V, which is a subset of V bar. This is U. That is, A is a subset of U. Between A and U, you have V and V bar. So this you remember. Next, let us have one glance. Many times you are asking, no, explain with the diagrams. So that is the reason. So here, how it will be. See, this will be a topological space. Under topological space, you have a T1 space. Okay, a T1 space, Hausdorff space, completely regular space, complete Hausdorff space, and metric space. Okay, like this they will be. That means these are all Hausdorff space is a T1 space. These are, first of all, these are all T1 spaces. So this is will give you the complete picture of T1 space, Hausdorff space, normal space, and completely regular spaces. Okay, students,
Okay, ma'am.
just go through this once, have an idea about the relations between T1 space, Hausdorff space, completely regular space, normal spaces, and metric spaces. See, next week is the last class, no?
Yes, ma'am.
So we will wind up next week. This all the what you call. I will explain all the theorems. 3 theorems are there. I will explain. Today I will explain 1 theorem. And next class I will explain another 2 theorems.
Okay, ma'am.
Okay, ma'am.
Okay. Okay, shall I move on to next one?
Yes, ma'am.
Yes, ma'am.
Okay, next one. So today we will do Urysohn's lemma. Before proving Urysohn's lemma, just how we have taken Lebesgue number and we proved Lebesgue theorem or Lebesgue covering lemma, we define a dyadic number. What is a dyadic number? It is a rational number of the form m by 2 power n. Why we have taken m by 2 power n? This 1 by 2 power n is a geometric series. So that is the reason you will have a finite quantity here. So here we define D, the set of all dyadic numbers, which is of the form m by 2 power n, where n is 1, 2, 3 up to m. 1, 2, 3 and so on up to infinity. M ekkadi nunchi vastundamma? M is 1, 2, 3. Ante enti? For example, niku m by 2 power n undanukondi, 1 by 2 power n undanukondi. N 1 aithe only you will have 1 by 2. Other one is 2 by 2 only you will get. Then 2 by 2 square, 3 by 2 square. Like that you will get. M is from 1, 2 up to 2 power n minus 1. Ante entandi? You should take, suppose if you get 2 cube vachindanokondi, in the denominator you have 2 cube, means m till where you have to take up to 2 power n minus 1. 2 power n minus 1 ante 2 cube minus 1 ante 7 anamata. 7 by 2 cube is a dyadic number. Okay. See, numerator is there, no? This numerator should not exceed the denominator. That is the rule. That is the dyadic number. Okay. Then the set D of all dyadic numbers is countable and is a dense subset of 0, 1. Dense subset of 0, 1 means every point is a limit point. 0, 1, that is, for any a less than b in 0, 1, there exists a rational number R, or there is R belongs to D such that a less than or less than b. So this is about dyadic number. And between any two real numbers, there exists a dyadic number. Dyadic number means it is a proper fraction, which is of the form m by 2 power n. So now look at this Urysohn's lemma. See, students, Urysohn's lemma, by writing and explaining, it takes so much of time. That's why I prepared notes. The total proof is 4 to 5 pages. Okay.
Okay, ma'am.
Proof is
Okay.
yeah. Proof is 3
Can you
to
share this, ma'am?
Emma. What?
Can you share these notes, ma'am?
Yeah. I have written. Actually, I have written from your material only, but it is more explanatory. I will share. Can I share in this class itself? Huh?
Okay, ma'am.
No, I think so. One of you send your number. I will WhatsApp these notes. Huh? One of you send a message to my WhatsApp number so that I will share these notes to you. Okay.
Okay, ma'am.
Then Urison's lemma. First of all, before learning Urison's lemma, you should have an idea of P1 space, Hausdorff space, regular spaces and all. See here. Let A and B be two disjoint closed subspaces of a normed space X. What do you mean by normed space X? Two disjoint closed sets can be separated by two disjoint open sets. Then there exists a continuous function f from x to 0, 1 such that f of x is 0 for x belongs to A and f of x equal to 1 for x belongs to B. Okay, so indirectly what we are saying, closed set, a normed space we want to a normed space we want to make it into complete regular space. Complete regular space. Done now? All the problems? 1 minute. Urison's lemma states that if A and B are two disjoint closed subspaces of a normed space X, then there exists a continuous function f from x to 0, 1 such that f of x is 0 for every x belongs to A and f of x is 1 for every x belongs to B. Okay. So just what are the concepts we are going to use? See, if C is a closed set and U is open such that C is a subset of U. And this is your U and this is your C. If C is, this is C and this is U. If C is a subset of U, then there exists an open set V such that C is a subset of V. Anyhow, we know that V is contained in V bar. Under U only you are going to have these subsets. This is the concept I am going to use. Is that okay for you? Hello?
Yes, ma'am.
Yeah. You have first C is closed and U is an open set. U is open set such that C is contained in U. Then there exists open set V containing U. Anyhow, we know that V is a subset of V bar. V bar ante gurtunda? V union points of V. So that is the subset of V bar. So we start with A and its complement, and we start with A and X minus B. Then you have A intersection B is empty. What do you mean by A intersection B is empty? Means A is subset of B complement.
There are no common elements in
A
A.
is contained in X minus B. Antena? Is this true from the theory of sets? Okay, mute your system now. Some disturbance is coming. Okay. So we start with A and X minus B. We start with A and X minus B. Since A intersection B is empty, okay, so you take like this, A, B. Total. If you know about sets, you can prove this easily. So you take A and X minus B. Since A is closed, definitely X minus B, he gave already. A and B are closed sets. In the statement itself, he has given. Let A and B be two disjoint closed space of a normed space X. So that is the reason B is closed means X minus B is open. So you apply the same concept. That's what I have written no here. If C is closed, U is open set, then there exists V such that V is contained in V bar, which is contained in U. This only I am repeatedly using. So since A is closed and B, X minus B is open, there exists an open set U half such that U suffix half and U half is open set such that A is a subset of U1 by 2 is the subset of U bar 1 by 2, which is the subset of X minus B. The same concept apply repeatedly because we are going to insert dyadic numbers. Again, you have A and U half are closed sets. This and this are closed sets because U half is open. It's a complement. It's a closure is a closed set. Since A and U half bar are closed and U1 by 2 and X minus B are open, again there exists open sets 1 by 4 and 3 by 4 such that A is a subset of U1 by 4, subset of U1 by 4 bar, subset of U1 by 2, which is the subset of U1 by 2 bar, subset of U3 by 4, U3 by 4 bar, subset of X minus B. Like that, we are going on constructing subsets. How it will be? First we take 1 by 2, then 1 by 4, then 3 by 4, again 1 by 8, 3 by 8, 5 by 8, 7 by 8. Like that, we are going on by arrows and continue the process to obtain open set UR, where R is M by 2 power N. See, you may have doubt why I have taken 1 by 8, 3 by 8, 5 by 8, 7 by 8. These are the dyadic numbers. I am making use of dyadic numbers. So for each dyadic number R equal to M by 2 power N, we have whenever R is less than S, you have A is a subset of UR, which is a subset of UR closure, subset of US, subset of US closure, subset of X minus B. Till here, if you understood, means almost we have done with the theorem. Students, are you following? Just
Yes,
go through this.
Yes, ma'am.
A is closed. A and B are two closed sets. So B is closed means X minus B is open.
Open.
So whenever there is a closed set and open set, there are two sets, V and V bar. See, this is the concept I am using here. Whenever C is closed, U is open and C is a subset of U. Then there exists open set V such that C is a subset of V is a subset of V bar, which is the subset of U. So I am taking with the help of dyadic numbers. ఇక్కడ చూడండి ఎక్కడెక్కడ ఇన్సర్ట్ చేస్తున్నానో చూడండి యారోస్ దగ్గర. ఇక్కడ మనకి ఏమేమి ఓపెన్ ఏది క్లోజ్డ్ చూసుకోవాలన్నా. ఏ ఈజ్ క్లోజ్డ్, యూ హాఫ్ క్లోజ్డ్. ఇఫ్ దేర్ ఆర్ 2 క్లోజ్డ్ సెట్స్ అండ్ ఓపెన్ సెట్, 1 క్లోజ్డ్ సెట్ అండ్ ఓపెన్ సెట్, you have to insert one more open set and closed set. Just look at this one.
Yes, ma'am.
ఇక్కడ ఇన్సర్ట్ చేస్తాను నేను. యారోస్ వేసాను చూసారా, అక్కడ ఇన్సర్ట్ చేస్తాను. ఎందుకు నేను 1/2 1/4 తీసుకున్నాను? డయాడిక్ నంబర్స్ m/2 పవర్ n. m ఎక్కడి నుంచి ఎక్కడికండి? 2 పవర్. ఇప్పుడు ఫర్ ఎగ్జాంపుల్ 2 పవర్ 1 తీసుకున్నారనుకో, యూ షుడ్ టేక్ 2 పవర్ n -1 అంటే 2 పవర్ 0 అంటే ఇక్కడ 1 వస్తుంది. m కనుక 2 తీసుకున్నారనుకోండి, 2 తీసుకుంటే m/2 స్క్వేర్. 2 స్క్వేర్ అంటే ఎంత? 4 కదా. సో యూ హ్యావ్ 3/4 అన్నమాట. అంటే m మాత్రము 2 స్క్వేర్ -1 ఉండాలి. ఒకవేళ 1/2 క్యూబ్ తీసుకున్నారనుకో, m/2 క్యూబ్ అనుకో, వాట్ ఈస్ ద వాల్యూ ఆఫ్ m? ఇట్ ఈస్ 2 క్యూబ్ -1. 2 క్యూబ్ -1 అంటే 7/8. అలా 2 క్యూబ్ -1 అంటే 7. లైక్ దట్ యూ హ్యావ్ టు టేక్ 1/8, 3/8, 5/8, 7/8. సో ఈ ఆరోస్ లో అన్ని చేసుకుంటే యూ విల్ గెట్ ఫర్ r less than s, A is a subset of UR, subset of UR dash. This you will get. Now, how you define a function? Now, define a function f from x to 0, 1 by f of x is 1. We define f of x is 1 if x does not belongs to UR. F of x is infimum of R belongs to D if x belongs to UR. UR అంటే ఏంటి? డయాడిక్ నంబర్స్. ఓకే ఓకే. Okay, ma, define f of x is 1 if x does not belongs to UR. If x belongs to UR, it is infimum of R belongs to D, x belongs to UR. ఇక్కడ D అంటే ఏంటమ్మా? which is the subset of 0, 1 because function range ఎక్కడి నుంచి ఎక్కడికి ఉంది? 0 to 1. So you have 0 less than or equal to f of x less than 1. That means f is well defined. So whenever you define a function, you have to prove that f is well defined. Now, what do you mean by x belongs to A? If x belongs to A, you have x belongs to UR. If x belongs to UR, it is the infimum of dyadic numbers. What will be infimum of dyadic number? 0. D is ranging from 0 to 1. For this, supremum is 1, infimum is 0. So if x belongs to A, implies x belongs to UR, which implies f of x is 0. And x belongs to B implies x does not belongs to B complement. So ఎప్పుడైతే x does not belongs to B complement, you have x does not belongs to UR. So you have x of x is 1. So in this way, I have defined function f of x. Now I prove that f is continuous. Okay, now I prove that f is continuous. So if you want to prove f is continuous, It is enough if we prove that the inverse image of any subbasic open set is open. I prove that inverse image of any subbasic open sets is open. So the sets of the form 0A or A1 for 0 less than A less than 1 will form a subbasic open sets in 0, 1. I prove that F inverse 0A, F inverse A comma 1 are open in X. Okay, I'll prove that they are open intervals. So what do you mean by X belongs to F inverse 0 comma A? Means F of X is less than A. F of X is, ante entandi, X belongs to this one means F of X belongs to 0 comma A. That means you have F of X is less than A. And what is F of X, Amma? If F of X is nothing but infimum of R belongs to D such that X belongs to UR less than A. This infimum F of X less than A means infimum is also less than A. So what do you mean by that? There exists R belongs to D such that X belongs to UR or less than A. That means you have X belongs to UR and F of Y less than or equal to R less than A. So you have X belongs to UR, where UR is a subset of F inverse of 0A that is contained in open set. Therefore, F inverse 0 comma A is open. And at the same time, if you have X belongs to F inverse A comma 1, that means F of X belongs to A comma 1 means you have A less than F of X less than 1. So F of X greater than A. That means we know, no, I told you between any two real numbers, there exists a real number. So we have proved that R and S are dyadic numbers. There exists two dyadic numbers R and S such that A less than or less than F of X for R and S belongs to D. That means you have X does not belong to closure of UR. Means X belongs to X minus UR, closure of UR complement. What is X minus UR complement? Which is a subset of F inverse A1. That means X minus UR is open in X. Therefore, you have F inverse A comma 1 is open. That means you have the inverse image of every subbasic open set is open. Hence, F is continuous. I proved Urison's lemma in a simplest way, and in textbook he has given in different way. In your material,
Yes, ma'am.
Urison's lemma he has given in different way. Almost it is also same. I explained in a neat way. What you call very simple, which is very simple. You can write this also. Okay.
Okay, ma'am.
Shall I explain once again?
Yes.
Okay. I proved in 3 steps separately. First of all, what is Urison's lemma? So before proving Urison's lemma, I want to prove this. So just I have marked it. One theorem is there, one result or in the form of theorem. A T1 space, capital X is normal if for any closed sets closed set A and open set U and open set U in X such that A is a subset of U, then there exists open set V such that A is a subset of V is a subset of V bar, which is a subset of U. This is good. Okay? Whenever in a normal space, two closed sets are separated by two open sets. So that is the reason that only I am defining in the different way. If a T1 space X is normal, if for any closed set A and open set U, there exists open set V between A and U. So making use of this, I am proving Urysohn's lemma. All of you, is this dyadic number concept is clear?
Yes, ma'am.
M by 2 power n, that is n can be 1, 2, 3 up to infinity. M is up to, M is 1, M is 2, M is 3, like that. Up to what is the before number? 2 power n minus 1. In the denominator, if it is 2 cube, numerator, last dyadic number will be 2 cube minus 1. Ante ippudu meer 7 తీసుకున్నారు కదా నాన్న. ఇక్కడ 1 by 2 cube is a dyadic number, 1 by 2 by 2 cube is a dyadic number, 3 by 2 cube is a dyadic number, up to 7 by 2 cube. So you will have so many dyadic numbers from 1 to 8. Okay? Next. Now, Urysohn's lemma states that if A and B are two disjoint closed subspaces of a normed space X, then there exists a continuous function f from x to 0, 1 such that f of x equal to 0 for x belongs to A and f of x equal to 1 for x belongs to B. What is this A and what is this B? These things also you only has to construct. How to take this? To construct these sets, I am making use of the above lemma. If C is closed and U is an open set in a normed space, in a normal space, in a normal space, then there exists okay ma, there exists normal space amma, normed kaadu, these sorry, normal space. If let A and B be two disjoint closed subspace of normal space X, then there exists a continuous function f from x to 0, 1 such that f of x is 0 for x belongs to A, f of x is 1 for x belongs to B. For this, I am constructing the sets using dyadic number concept. So let us start with A and x minus B. Here you have x, A is closed and B is closed, means x minus B is open. So there exists a set U1 by 2 such that A is a subset of U1 by 2, which is a subset of U1 by 2 bar, which is a subset of x minus B based on this result. If T1 space X is normal, then for given closed set A and open set U, there exists V such that A is a subset of V is a subset of V bar. Here I cannot take general set for the proving the theorem. So I took U1 by 2, U1 by 2 bar. Okay, ma? Where it is open. Now you have, see here, A is closed. U1 by 2 bar is closed. U1 by 2 closure is closed. Again, you can find two more sets between A and U, isn't it? Okay. So again, you have U1 by 2 is closed. X minus B is closed. Between these two closed sets, once again, you can find. So you have A is U 1 by 4, subset of closure of U 1 by 4, which is the subset of U 1 by 2, subset of U 1 by 2 bar, which is the subset of U 3 by 4, which is the subset of U 3 by 4 bar, which is the subset of X minus B. So I am arranging the sets. Now repeat the above process to get to open sets U 1 by 8, 3 by 8, 5 by 8, 7 by 8 in the places shown by arrows. ఇక్కడ పెట్టుకోండి, ఎక్కడైతే arrows చెప్పానో అక్కడ పెట్టుకుంటే by continuing this process you can find for each dyadic number m by 2 power n with the following property r less than x. Whenever r is less than s, you can find ur, which is a subset of ur closure, which is a subset of us, which is a subset of us closure between a and x minus b. These places I am not replacing, that only in between only I am inserting the sets. Now how you define function? Define a function f from x to 0 1 by f of x is 1 if x does not belongs to ur, equal to infimum if x belongs to ur. Infimum of dyadic numbers. What is the infimum of dyadic numbers? 0. Supremum is 1. So because all the dyadic numbers lie between 0 and 1, the function range function is defined from x to 0 1. Now you understood why I have taken 3 by 8, 7 by 8 like that. All should be less than 1. Range is 0 1. So f values lie between 0 and 1. Therefore, f is a well-defined function of 0 and 1. Now, what do you mean by x belongs to A? Because A is a subset of UR, subset of UR closure. So when x belongs to A, you have x belongs to UR. So f of x is 0. Suppose, what do you mean by x belongs to B? X does not belongs to B complement, that is x does not belongs to UR, means your f of x is 1. When x does not belongs to UR, f of x is 1. So it is the completion of defining the function f of x. Now we prove that the function f is continuous. If you want to prove function f is continuous, చెప్పాను గుర్తుందమ్మా, whenever G is open in Y, you have to prove f inverse G is open in X. Avuna? The same concept only, nothing but we prove that inverse image of any subbasic open set is open. The inverse of any subbasic open set is open. So the sets of the form 0, a comma 1 for 0 less than a less than 1 form a subbasic open sets in 0 1. So we prove that f inverse 0a and f inverse a1 are open in X for 0 less than a less than 1. Now x belongs to f inverse 0 comma a means f of x is less than a, which implies f of x is f of x less than a means you get f of x is infimum of r belongs to D such that x belongs to ur, that is less than a. That is, there exists r belongs to D such that x belongs to ur, such that x belongs to ur and r is less than a, because here infimum kadama, infimum is less than in element. So infimum is greater than lower bound. And x belongs to ur and f of y less than or equal to r less than a for all y belongs to ur. So you have x belongs to ur, which is a subset of f inverse 0 comma a, and ur is open in X. That means you have f inverse 0 comma a is open in X. Open in X. So also X belongs to this one means the other one f inverse a comma 1 is also open in X. So you have the inverse image of every subbasic open set is open. Therefore f is continuous. So in a normal space or in a normal space, it is possible to construct a function f such that f of x is equal to 1 and f of x is 0, which will give you every normal space is completely regular. Every normal space is completely regular. Why? Because let X be a normal space and X belongs to S. F is a closed set not containing X. Then what will happen? Then X and capital F are disjoint closed sets in X. So what do you mean? By Urysohn's lemma, there exists a continuous function such that f of x equal to 0 and f of x is 0 for x belongs to x and f of y is 1 for y belongs to f. Therefore, x is a completely regular space. So, what for we proved Urysohn's lemma? To prove, to show that every normed space, every normal space is a completely regular space. By making use of Urysohn's lemma, it became very easy to prove that X is completely regular space. Students, if in exam, if this theorem comes for 10 marks, you have to write Urysohn's lemma. Every normal space is completely regular. For that, first we prove Urysohn's lemma. Students, what all the concepts I taught, are they clear to you? But Urysohn's theorem, whatever I explained, it may be difficult concept. You have to give 1 to 10 readings and first of all, you read the proof for 3 to 4 times. Then you start learning. Then only it will be clear to you. Otherwise, you cannot follow. Okay?
Okay, ma'am.
Okay, ma'am.
Yeah, if you send a WhatsApp number, in this 17 pages, there are 3 important theorem. This T's extension theorem, it will take 1 hour. And one more class, I will take Urysohn's embedding theorem. Okay?
Okay, ma'am.
Yeah, that's what for yourself only I have prepared your notes in a easiest way. Okay?
Okay,
Okay,
ma'am.
ma'am.
Thank you, ma'am.
Notes I will share in the WhatsApp.
Okay, ma'am.
Okay, ma'am. Thank you.
Okay. Thank you. Shall I leave the class?
Yes,
Yes,
ma'am.
ma'am. Thank you, ma'am.
Yeah.
Excuse me, ma'am.
Yeah.
मैम असाइनमेंट कैसे सबमिट करना है?
असाइनमेंट कॉलेज को जाके सबमिट करना.
ओके मैम, स्टडी सेंटर में है ना?
हाँ, स्टडी सेंटर ओनली.
ओके मैम, थैंक यू
When
मैम.
was the last date, ma'am?
No idea, Amma. For me, no idea.
Okay, ma'am.
Because you have to see in the university website only. Okay?
Okay, ma'am.
Shilpa, I am saving this number 9014817045. I am sending these notes to you. Okay?
Okay, ma'am.
I will send. Okay, if you form a group and share the notes in the group. Okay?
Okay, ma'am.
Okay. Bye. Next week is the last week, last class. Only 2 classes we are getting. So I'll revise and complete these 2 theorems so that entire syllabus get over. Okay?
Okay, ma'am.
So, and also what I am doing is I have not left any chapter from your syllabus, but whatever you feel easy, you learn them. Okay?
Okay, ma'am.
Okay, bye.
Bye, ma'am. Thank you, ma'am.
Thank you,
Welcome.
ma'am.
Shilpa, are you group in there?